Hello and welcome back to additive manufacturing and 3D printing using Ansys SpaceClaim. This is week 4, and in this lesson we'll be covering the different 3D printing technologies. In the previous session we discussed the following: advanced pull, sweep pull, parameter groups, move tool, linear pattern, and the mirror tool. Up to now, we've just been discussing how we can create the 3D models that we'd later use in the 3D printing environment. However, all of this is dependent on the 3D printing technology that we choose and their limitations. In this lesson, we'll be covering the different 3D printing technologies. These will be selective laser melting, selective laser sintering, fused deposition modeling, stereolithography, laminated object manufacturing. The learning objectives for this week are going to be to learn about the most common 3D printing technologies, some of their advantages, disadvantages, and the applications and specific uses of all the different technologies. At the end of this lesson, you will be able to identify the correct technology to use depending on what you wish to achieve, your situation, and the application. So let's get started with the 3D printing technologies. As was briefed at the start of this course, there are several 3D printing or additive manufacturing technologies and techniques that vary depending on material used and depending on the layer bonding methods. Right here, we will explore these technologies in more depth. Some of the most common examples of the technologies for 3D printing are selective laser melting, selective laser sintering, fused deposition modeling, stereolithography, and laminated object manufacturing. There are also other 3D printing methodologies, however, their applications, use, and commonality are not that applicable and they're not that widely used, so we'll disregard them for the purpose of this course, as we'll only cover the most common ones that you will meet in day-to-day applications and in industry. So let's get started with selective laser melting and selective laser sintering. So what is selective laser melting and selective laser sintering? And why are they generally grouped together? Well, first off, they are generally grouped together because usually the machines and applications used in this type of additive manufacturing process are relatively similar. That is, they both use a powder bed material which is melted by a laser beam to create the object that we desire. So how does this work? First off, as you can see on the right, you have the workspace or work area that is depicted by the center structure where the piece being printed resides. What happens is there is a platform on this area which has to be kept fed with powder material. Generally, this powder material is metal filings. So pretty much what you get is very fine metal powder that is deposited from the powder material store on either side of the workspace by a roller. So how this works is you get a little bit platform on the left and on the right, which moves up to sort of extrude a bit of metal powder, which is moved and deposited by a roller onto the workspace in a controlled layer of specific thickness as the roller moves back and forth from the left side to the right side and back from the right side to the left side. The platforms on the left and on the right move up to allow for material to be shifted onto the workspace. It is similar to how when you are making a pastry out of dough and you squish with the roller the little dough ball to flatten it out across your countertop. The same concept applies to this, where you get your metal roller and you push out this powder and spread it evenly onto the workspace. Once you have a fine layer of powder on the build platform, a laser above, guided by mirrors or directly, shoots a beam onto the powder in specific points to melt the powder in the specific shape depending on each layer. Once a layer is complete, the main build platform in the center moves down by a layer to allow the roller to deposit a new layer of powder material on top of the just finished and completed layer to start the subsequent layer. Then the laser subsequently melts the second, third, fourth, fifth layer, and so on and so forth until you end up with a finished piece. What is the difference between selective laser melting and selective laser sintering, though? In selective laser melting, the laser completely melts the powder for each layer. However, in selective laser sintering, it only partially melts each layer. Now, you'd be thinking to yourself, why would you only want to partially melt a layer? So what is the purpose of selective laser sintering? Well, it actually takes a lot of energy and time to completely melt a layer. So, unless you actually want a structural component that will be used in end applications, in which you would use selective laser melting, you would use selective laser sintering just for prototype parts where the structural properties are not that important. However, in these applications, generally they are more time sensitive. So you do not want to waste the time completely melting the layers. You want to quickly create the piece for prototyping purposes. This partial melting of layers is what is called sintering, where selective laser sintering gets its name from. So, what are the advantages of selective laser melting and selective laser sintering? The advantages are, considering you only melt some of each layer to create the cross section of the part you are building, the powder bed material that is not melted on each layer can be reused in subsequent builds. So pretty much, when you finish building your piece or object and you remove it from the 3D printing machine, you can remove all the excess powder bed material and feed it back into the material bank on either side of the workspace to be reused in future prints. This is good from a recycling and ecological standpoint, and also from a monetary standpoint, as you do not get as much waste material. So this is good as you do not end up with scrap material and you can reuse some of the expensive build material again. There is no need for support structures when using selective laser melting and selective laser sintering. This is because if we scroll back, as you can see on the diagram, in the center portion, the workpiece, each layer of it has powder bed material in each layer. So pretty much every subsequent layer that you build will be supported by the previous layer powder bed material. So in essence, you don't need to add any additional structures underneath to support overhangs or long bridges because the powder bed material itself adds supporting structures or can act as a supporting structure. In other 3D printing technologies, usually there is an air gap between the layer overhangs. So gravity pulls down on each layer and can cause different problems. However, in this scenario with SLM and SLS, you do not get such issues. Selective laser melting and selective laser sintering are one of the few technologies that can actually print using metal as the primary base material. Most often than not, in 3D printing, we end up using photosensitive polymer or different kinds of plastics or laminations in the 3D printing process. So SLS and SLM, fortunately, are one of the few technologies which allow you the privilege of using metal as the base material. Another advantage is SLM and SLS, because of the laser resolution they use to melt the material, they have a very accurate resolution. You could say it is pinpoint accuracy because the laser beam can be very narrow and very precisely controlled. Whereas other technologies, they use a flow of polymer or plastic, which does not have that good of a resolution, as we'll see later on. Another advantage is selective laser melting produces quite strong parts, as each layer is melted subsequently onto the next. So, using metal as the base material, you can end up with really strong parts that can be used in end-of-line applications in industry, not just as prototyping technologies. However, if prototyping is the purpose you are after, selective laser sintering can offer the speed desirable to produce prototype parts quickly and accurately, however, compromising slightly on the strength of the parts produced. Now that we have covered the advantages, let's go over some of the disadvantages that SLS and SLM have. The main disadvantage for these technologies is the expensive equipment. Considering the price of some consumer available 3D printing equipment for fused deposition modeling or stereolithography, which can range in the hundreds of pounds or hundreds of dollars. On the contrary, selective laser melting and selective laser sintering equipment can cost in the tens of thousands of pounds and dollars, which is by a factor of at least 100 times more expensive. In addition to the expensive equipment, you also have quite expensive powder material, considering that the powder material needs to be accurately controlled, so all the powder particles are roughly the same size and dimension for consistency of prints. Really accurate manufacturing processes need to be employed when producing the powder for these applications. In addition to this, considering that you are using a laser to melt some of this metal powder, and considering the oxidation properties of certain metals such as aluminium, which oxidizes relatively easily and quickly into aluminium oxide. Sometimes inert gas needs to be introduced into the workspace environment in order to avoid contact with oxygen during the melting properties to avoid unwanted oxidation of any part of the workpiece produced. This inert gas obviously cannot be reused in the context of production, so you would need a consumable supply of inert gas to be readily available and continually replaced and replenished whenever you produce any pieces using this technology. Obviously, this inert gas adds to the cost of production and to the complexity of the manufacturing process. Considering that we touched upon some of the complexities of this manufacturing process using SLS and SLM, it's also very important to note that certain health and safety procedures and equipment will be required when handling the powder and with the gas produced and used during the melting process. Considering that this powder is very fine and can pose several health risks if aspirated, if you breathe in the powder, this is not good for you, as is similar to sanding technologies when you use blast sanding on certain parts and you have to use a respirator or a gas mask to avoid inhaling the sand. In this scenario with selective laser melting and selective laser sintering, you have to apply the same cautionary procedures to avoid inhaling either the powder bed material or inhaling the gas that is used in the manufacturing process to avoid oxidation. Considering this, not everyone or anyone can get started with selective laser melting or selective laser sintering off the bat. Special training regimes and safety precautions need to be learned and adopted before utilizing such equipment and machinery, limiting its applicability more to an industrial role and section rather than a consumer or hobbyist role. Now that we have covered the advantages and disadvantages of selective laser sintering and selective laser melting, let's cover some of the applications of these technologies. In the industrial sector, you can use this technology to create prototype parts to test certain designs. For example, in the aerospace industry, if you want to test different aerodynamic designs, you can use selective laser sintering to quickly and effectively produce these designs physically and put them in a wind tunnel to test the aerodynamic properties. However, if you want to check structural properties of certain part geometry, you can use selective laser melting to create some prototype parts for this application. In addition to prototype parts, because of the structural properties of selective laser melted produced parts, you can actually use these parts in end user applications, such as custom parts. As an example, let's say you are a person who is restoring a classic car from the 50s. Obviously, because of the age of the vehicle and the parts you are using, it might be very difficult to find replacement parts for your application, especially for decorative or trim parts, such as a badge or emblem. However, using selective laser melting, if you can produce a 3D CAD model or a representation of the part that you wish to have, you can send that off to be 3D printed. Considering you won't need so many parts for your application, most often you would need just one of these parts for the application. So this is a perfect example of this. Generally, automotive manufacturers or manufacturers in many other sectors don't tend to produce one-off parts for applications. If there is not a mass production incentive or a need for mass-produced parts, generally such parts would either be very costly to pre-produced on demand or on order, or they would not be produced at all. Also considering that most metal parts are either cast or stamped and pressed using dies. Certain dies from the original application might not be available anymore, or they might be discontinued. For such applications, you can use selective laser melting to produce replicas and one-offs at a much lower cost. Another industrial application would be creating tools for special tasks, such as jigs and fixtures. Jigs and fixtures are pretty much a manufacturing or production guide that you can use to either set parts or assemble parts correctly. Another type of special tooling that you can use is, as an example, again from the automotive industry, certain motorcycles used during World War II in the United Kingdom, they did not use the metric system in their production. So you do not get, as an example, 8mm or 10mm nuts and bolts. You get either imperial unit measurements used or some other specific type of special measurements used, which for different specific purposes at the time of the war sort of disincentivized the Germans from actually reproducing or being able to reverse engineer certain components, as they were not be able using their metric tools to be able to disassemble certain components off of the motorbikes. Considering that the tools that were used are now discontinued, it might be tough to be able to actually work on such vintage pieces of machinery. In this application, if you know, or actually by measuring the bolt across face measurement, you know exactly what dimension of tool or socket that you need to use. You can model this in your 3D modeling program and 3D print an actual tool or socket to be used for the application to actually disassemble and reassemble the parts that you need to service. In addition to industrial applications, you also have medical applications for SLS and SLM. This is generally used to create custom-made prosthetics from 3D scans. For an example, if someone breaks a bone and they need to have a specific cast or a replacement part of their bone to be placed, so let's say if someone suffered a workplace injury and they lost a piece of the bone in their skull, selective laser melting could produce an exact fit of the missing bone from metal that could later be used in a surgical application to be implanted into the patient. This allows us to create custom-made prosthetics very quickly and fast, and considering the material that we can use, such as lightweight aluminum that can be later sterilized as well and is structurally sound in a medical application, this is very applicable to the medical sector and very useful in the medical sector.